Thank you.
So with this, it is my great pleasure to introduce today's keynote speaker, somebody who whose work sits at the critical intersection between cybersecurity, hardware security, and the future of secure computing. And I would like to start this with a short anecdote, and I hope we can get here, keynote. So I would like to start it with a very short anecdote from my arrival on Sunday. So I landed at the LA airport and made my way down to San Diego. And one of the first things I noticed on the highway coming down here was this traffic sign, and it said Sepúlveda Boulevard. And I thought this is actually a very nice supporting sign for the choice of our keynote speaker. With that, so let me introduce and welcome our today's keynote speaker, Dr. Johanna Sepúlveda, who is a senior expert and a technical domain manager for quantum and quantum secure technologies at Airbus Defense and Space. Whether it's about securing next-generation avionics, protecting military-grade communications, or designing the future of cyber-resilient hardware, her expertise shapes the very foundation of secure computing. Johanna is no stranger to NDSS. She has in the past acted as an NDSS TPC member. She received her Masters of Science and PhD degrees in electrical engineering and microelectronics from the University of Sao Paulo in Brazil. And she was a senior researcher in the area of security and emerging technologies at the University of South Brittany and at INRIA in France, and at the Technical University of Munich in Germany. Her career has spanned both academia and industry, giving her some form of a unique perspective on bridging the theoretical breakthroughs with real-world applications. In her role at Airbus, she also acts as the chief engineer of different European quantum initiatives, such as the European Quantum Communication Infrastructure, EuroQCI, and she serves as the vice chair of the Strategic Advisory Board of Quantum Technologies for the European Commission, and is the leader of the Strategic Industry Roadmap at the European Quantum Industry Consortium, QIC. Hamid and I, we reached out to her to hear about security topics that are relevant for Airbus Defense and Space, also hearing about the industry's vision for security in this important sector, and ideally hearing about some understudied areas that need more attention from the security research community, including, but not limited to, quantum communication and computation. And I just want to mention that there are 2 papers accepted this year at NDSS as well that are quantum security papers that will be presented in 2 sessions on security protocols and on side channels as 1. So without further ado, please join me in welcoming Dr. Johanna Sepúlveda on stage.
Good morning. Thank you so much for the invitation. It's amazing to be here. And I think it's in a timely manner because, as you know, it is a pleasure for me to bring the quantum technology to NDSS in 2025, the year where UNESCO nominate or state the year of the Year of Quantum Science and Technology. So during all 2025, there are going to be several events, several demonstration of this technology, fostering the further development, not only of the technology, but also of how we bring these quantum technologies to real applications. So the intention of this talk is to describe the quantum technologies and also the 3 different pillars. That means quantum computing, quantum sensing, and quantum communication, focusing on the interest of NDSS community, and also it is a call for the community to help and support in the advancement of this technology, to bring from the science for this kind of lab demonstration into some more applied technology. So first of all, I'm going to talk of Airbus. It's not going to be an advertisement, I swear, but it is more that you understand what is our vision and why we are concerned about innovation and about the quantum technologies. So many of you have recognized Airbus for the very efficient and amazing aircraft on the commercial airlines. But Airbus is not only civil avionics. We have different branches. It also includes a huge branch of helicopters, not only for civil but also military applications. And it has a third branch of defense and space. In the parts of defense, Airbus produces different artifacts and infrastructures that are used for secure different governments. In addition, in the part of the space, we develop not only satellites, but also optical ground station for different applications, including Earth observation, communication, and navigation. And of course, we are also service providers for secure comms for different sectors, with a very strong branch of cybersecurity, of course. So, of course, as you see, we have different assets in terrestrial, space, or space domain, and we focus and deal on the part of security and how we can offer safety and security to our customers. So let's start for the quantum technologies principles. I swear I'm not going to bother you with the part of the physics, but most to give a wide understanding of why it is attractive to the different pillars. We are going to see the principal and general overview. So quantum technologies, we already now are in the second revolution, but we already have the first revolution in the early 1900s. So there were three different experiments or proof that shaped the first and solidified the concepts of quantum mechanics. The first one is the experiments of Young and as well the photoelectric effect, in which they show the duality of the light, of the particle, wave-particle duality. This is very interesting because it will show the different quantum phenomena that we're going to see in the next slide. We also have the second main concept that it was shaping the quantum, and is the uncertainty principle of Heisenberg, in which if you know the position, you don't know the speed, and the contrary, if you know more about the speed, you don't know about the position. And the third one is the Schrödinger function, that it was a function that it was able to describe the state of quantum mechanical systems. So this shaped the first revolution of the quantum mechanics, and all these principles were used to further go out to the lab and, for example, develop the transistor to have a strong impact in real application. Quantum phenomena, there are several, but the two main that really are very interesting and can be used in different applications. The first one is superpositioning, where in quantum states, all states are possible unless you measure. When you measure, you collapse the state and you have a single state, and then you can replicate this kind of measurement several times. And we have the entanglement, in which somehow the particles are somehow related. So in the part of the superposition, you might recall the known experiment of the imaginary experiment of Schrödinger, of the cat, in which a cat in a box can be alive or dead together with a poison. And you only will be able to know if it is alive or dead when you open the box and you measure it. But an entanglement, it was demonstrated for different experiments, how the different particles, somehow they can be correlated, and even if they are very far apart, they have some relation. So somehow some effect in one particle will have an effect in the other entangled particle, and you will have some teleportation of information. Due to this demonstration of experiments of the entanglement, it was that in 2022, these three physicists get the Nobel of Physics, And this kind of principle, for example, it is very attractive because it helps not only to the teleportation of information, but also on the manipulation of a huge quantity of information. Also, we saw that in 2023, 3 physicists, again, in the area of quantum get the Nobel Prize because they create a method that allows to further understand the Schrödinger equation and understand the dynamics of the quantum mechanics. So it is a very relevant topic that currently more and more they are getting into real applications. So based on these kind of principles, they are creating 3 pillars of the technology. The first is the quantum computing, in which using superposition and entanglement, we are able to create different kinds of computing machines that encode information as quantum information called qubits, and they are able to overcome and to have a better performance that the computational performance that we can have with the known supercomputing. The second pillar is the quantum sensors. With these quantum sensors, we measure physical phenomena, but using this quantum phenomena that I described in order to have more accurate, more reliable sensors. And the third is the quantum secure communication. With quantum secure communication, we can create new networks, new ways of exchange information in an ultra-secure way, since the quantum information cannot be copied and any drop will be detected. I also always include the post-quantum cryptography because, yes, the post-quantum cryptography are different algorithms that are resistant to quantum attacks, but they are not quantum in nature per se, but they're part of this ecosystem, this landscape. And we are going to describe now in the different parts of the talk which are these pillars about how they can contribute to the networks in general and how they reshape the future. Now that you understand a little bit of the context worldwide, so for each one of the pillars, we have different champions. So quantum technologies are considered strategic for all the nations. And there have been a huge investment in this topic. When we talk about quantum computers, we thought currently it is heavily leading by USA. If we talk about quantum communication, China is leading this area. And if we talk about quantum sensors, Europe is leading this part. This is consequence of huge investments. So these are this is a report of McKinsey in 2023. Compared with the first report of McKinsey in 2021, what we can have or we can observe is a huge diversity of an inclusion of new countries. China, it is currently investing, it is reported the investment of 15.3 billion. Note that it is just the governmental funding. We have Germany in second place, USA is in fourth place, but when we consider all the private investment, USA, for example, go to the second place. But anyway, it is considered strategic, and it is a race for further give the applicability of these technologies into the real world. In addition, we can see that this has grown the interest of the development of different business startups. We know that, for example, in quantum computing has the most amount of investment and also has created a huge amount of startups in few years. The second pillar is the quantum communication, and the third one is the quantum sensing in the names, in the numbers of startups, which is curious because the quantum sensing is the most advanced quantum pillar. And we also see that they are not only industrial interests, but also the development of basic science, of development of patents in this area is also increasing. In Europe, it is also very important to measure which is the result of the investment on quantum technologies. So for example, in the advisory board that I am vice chair, one of my missions is to hold this book of the key performance indicators on quantum technologies in Europe, in which we have defined a set of metrics in which we can evaluate how Europe is going in these technologies. The report is open and is available in the Quantum Flagship website. But it's not only about science. It is also, quantum will have an impact in several markets, as we are going to see. One of these is defense as well. So in the part of defense, it is foreseen that the quantum technologies will have, or will offer some advantage in the military domain, and that is why they are also being integrated as part of computational capabilities, exploration of secure communication, and development of new sensors based on these principles for the defense part. And this is our footprint. So Airbus currently is working in the 3 different pillars. We have different positions. As you can see, for example, in the part of computing, we are users of these quantum computers, identifying which are the kind of applications that can benefit for these kind of machines. Part of sensors, we are integrators and service providers. In the part of communication, we are also integrators, service providers, and designers of these networks. So now let's go to the quantum computers. So quantum computers, this is one of the quantum computers. This, as I mentioned, is a different kind of machine based on these quantum principles that are able to perform certain operations in a faster way, more faster than, for example, the powerful supercomputers. But why they are used or where they are used? So first of all, what we have to see is that the quantum computers are not a general purpose computers. They are just used for certain applications, and there are 3 applications. The first one is the simulation of complex systems. Helping to model different kind of environments and having very fast answers in these computers. The second is the optimization of multi-objective problems, and that includes also the part of machine learning. These kind of computers are very interesting for machine learning since they need very fewer data for learning, and also they can learn in a faster way. And the third one is the security. So with these quantum computers, yes, they are good for this application, but also represent a threat. With the quantum computers, it is possible to impact the security of the symmetric cryptography and also break the public key cryptography. When this kind of threat will appear, so according to the different national security agencies, it can appear at any moment, but it is foreseen that in a timeline of 10 years, this computer will be ready to attack. So what we mean that what the threat is about. So when we talk about the public key cryptography, currently it is considered secure because we will need a long time in order to break or solve these hard mathematical problems. Then in quantum, the problem is that there are 2 quantum algorithms that can be executed in these quantum machines and will have an effect on security. The first one is the Grover algorithm designed in 1994 by Professor Grover. The impact is that this kind of algorithm is able to halve the security of symmetric cryptography. So that means that in order to keep 128 bits of security, we will need to use AES-256. So it is impacted, but the symmetric algorithms can be patched. It is something that will not happen with public key cryptography by executing the short algorithm. So these kind of hard mathematical problems that are realized or are the base of RSA elliptic curves can be solved in a few seconds, and in addition, the hashes also will be impacted. So that is why new algorithms must be found, or new ways to do, for example, key exchange, signature must be found. Regarding quantum computing technologies, there are different kind of underlying qubit technologies. So there are different kind of computers. Each one of these computers are foreseen that they are good for certain applications. So for example, in Airbus, we have benchmarked several computers. There are some that are better for machine learning, others are better for optimization, etc. Currently, it's not yet set which is the champion technology. So different nations are invested in, first of all, a diverse kind of technologies. Focus, for example, in USA, we have a huge impact in neutral atoms, but also in superconducting. China, it is also focusing on photonics and superconducting, etc. And in Europe, we also are working in trap ions, superconducting, photons, and neutral atoms. How is the evolution of this kind of machines? We have now recently seen how they are speed up in the computational capability of the different computers. In order to break the cryptography, there will be required at least 1,000 logical qubits. The problem now is that this kind of quantum information is very susceptible to noise. So in order that we have one logical qubit, we need several physical qubits in order to apply some error correction capabilities. And according to this technology, this can be varied from some dozens to several hundreds. But if we have 100 logical qubits, they already can be a threat for the cryptography. Now, regarding the applications, here are the 10 top applications that are foreseen that have a quantum advantage. That means that the quantum computers can do better than the classical computers. And that includes artificial intelligence, machine learning. So maybe an option to increase your acceptance rate for the next NDSS. But also we have cybersecurity. And the 8th for you is also interesting. That is the Internet of Things that is mostly about the scheduling, for example, of the space load with this kind of algorithms that can run in quantum computers. For NDSS, I think these are some of the applications that can be attractive. What I can say is that, for example, in Airbus, we are exploring together with our customers this machine learning in terms of scheduling of tasks in different networks, as well as anomaly detection and in different pattern recognition areas. So this was about quantum computing. We know that they have still, these machines still, they have some limiting in their processing, but the way to use it is using in a hybrid way with HPC capabilities together with a coprocessor of quantum computer. And the idea is to further explore their application and how they can better outperform and have some advantage for some application. Now we go to the part of quantum sensing. So quantum sensing is the most advanced quantum technology. These quantum sensors, as I mentioned, they use some quantum effects in order to measure some physical quantity. What they bring to the table is that these kind of sensors are more sensitive, they offer a high precision, high stability, and low maintenance. And that is very attractive, and they also enable very interesting capabilities I'm going to show later on. One of these, the interest, for example, in the security area is how to use these kind of sensors in order to resist jamming and spoofing attacks. And for example, in the military part, how to speed up the ODA loop, that is observe, orient, decide, and act. If you speed up this kind of ODA loop, you will have a higher rate of success in the mission. So with these sensors, they have been proven very efficient to work even and provide, for example, the navigation of system, even if you don't have the GNSS or Global Navigation Satellite Systems signal. So these offer not only reliability, but also will offer different capabilities in the field. And that is something that is very of a huge concern worldwide, mostly what it was seen now in the Ukraine. where there are several jammers that are somehow degrading the success of missions in this area. In addition, jammers and spoofers are currently not only a very wide, but also very cheap attack. And here, for example, in this kind of website, you can see how the different jam and spoofing attacks, and you can also imagine the effect in the electronic warfare impact. So regarding quantum sensors, here I can talk about 6 kind of sensors that are very attractive. So one is the atomic clocks. With atomic clocks, you can have the most accurate timekeeping devices ever created. And this has impact it can be very attractive for the part of synchronization of systems. It is foreseen to be, for example, to be useful for the 5G, 6G kind of communication. We have the quantum magnetometers that measure magnetic field with high precision. In the area of navigation, this is very attractive because you can create maps based on the magnetic field of the Earth. So you can create a navigation system without any GPS, for example. You can have quantum gravimeters. With these quantum gravimeters, you can have a very accurate and better visibility of what is happening under Earth and under sea. You also have quantum inertial sensors that also offers a better way of navigation and without any drift and without any maintenance, what is very attractive. Quantum electrometers that they are foreseen to be the base technology for next generation antennas, and photon detectors where we'll allow to see in very 3D images and across different obstacles. So you can see behind obstacles, which is very interesting. One thing that is a challenge, how to use all these quantum sensors together with the traditional sensors and fusion it into networks, because at the end you want to get this kind of data to some users. Quantum sensors, they're already a reality. So here you can see the different TRLs, that is technology readiness level. When it is technology ready level 9, that means that they are already commercially available. So we see that there are already several quantum sensors that are commercially available. We have several codes. We have also a big bunch on early and advanced prototypes. So it is something that is real and it's already is used, for example, in medical devices, etc. Some of the applications that are very interesting is, like, for example, how you can make the gravity cartography with using these quantum gravimeters, so you can really see what is under the Earth and in the subsurface, not only on the ground, but also on the sea. Another example is the quantum inertial navigation, and it is how you can, for example, use these quantum sensors together with traditional sensors and have some reliable assistance for navigation in case of any error, etc. You have some resilience based on this, which is important not only for commercial but also military purpose. And of course, in the part of security, these kind of sensors also offers a new degree of sensitivity, being able to explore new kinds of advanced side channel attacks. So this is also something that it is very relevant for the community. So now we close the part of the quantum sensor by knowing that they are already advanced, they are already there, and they offer several applications, and it is really mandatory to bring these kind of capabilities to some users through, for example, networks. Now let's talk about the quantum secure communication. So I recall what I was discussing in the beginning, which is the quantum threat. So we have different applications with their different life cycles. It is expected that in 10 years, a quantum computer arrives. That means that when the quantum computer is able to break the crypto arrives, we need to make a transition to quantum secure mechanisms. For previous crypto transitions, we know that crypto obsolescence is very difficult to manage, and it will require some time to adopt new methods, new techniques in order to protect the systems. So that means that during all this time, systems will be exposed to attacks. In addition, we know that currently different attackers are recording the secure communication, and they can decrypt it later with the quantum computers. So that is why it is relevant to adopt quantum secure mechanisms now. And this brings several risks, but also opportunities. So this was already an advice the national security agencies gave in 2016, go and think on quantum secure mechanisms, and this advice has been embraced by standardization bodies like NIST, governments, companies, etc. If we talk about the defense part, so one of the challenges that we have is that in the defense area, it is characterized by assets that are deployed in the environment long time, so we require long-term security. In addition, they are characterized by different levels of criticality and security levels. They are heterogeneous, not only in the way that they process and store information, but also in the way that they communicate. They have several protocols, underlying physical technologies, etc. And in all this environment, and you can also think on also in other communication and commercial environments, you need to adopt the quantum secure solutions. Currently, there are two technologies that offer quantum secure. The first one is the quantum communication with the first service that will be quantum key distribution. This quantum key distribution, what it does is that it exchanges a secret key between different parties in order that these parties can use this key later on for secure communication. What it offers is that these quantum channels are ruled by two physical properties. The first one is that the quantum information cannot be copied, and any drop will be detected. And this is especially attractive for certain applications, such as governmental communication, critical infrastructure, and healthcare and finance, for example. However, of course, it has some disadvantages. It has a very low throughput, and I'm going to explain later why. So now it is used just for key exchange. It is expected that in the future, with the increase of the throughput, it can be used for the quantum internet, linking all the different quantum assets into this global network based on quantum links. Also, in order to deploy this infrastructure, a new network will need to be used, and this is highly cost. It also needs scalability and resilience, and it also, as any security, it is prone to implementation attacks. We have post-quantum cryptography, so there are different kind of math, different kind of algorithms that are resistant to traditional and to quantum computers, and they can be deployed with our current technology. The advantages is that currently it has different kind of functionalities, key exchange, signatures, verification, etc. It can be already be deployed in our computers with our current and traditional technology. It is have a good scalability, as well as a different portfolio of mathematical problems, and it is a target of several standardization efforts. Disadvantage, it is prone to the implementation attacks. It needs to build confidence, and in addition, and it's based on mathematics. We don't know if in the future we have a SHORT-2 algorithm that will be able to break these kind of algorithms. The solution, and what it was already advised by the different national security agencies, is the transition to quantum secure should be in a layer approach. That means that first we are going to have a quantum, a classical security. On top, we will put a post-quantum crypto, and for certain applications, we will have the quantum communication layer. When should be this transition made? It depends. In USA, they have the roadmap of making until 2035. In Europe, it is expected to be until 2030. So let's talk about post-quantum cryptography. So we have different kind of problems. Each one are based or have different advantages and disadvantages. They are not a single best algorithm, but they offer or they can be mapped in different applications. What I want to see, or what I want to show, is that here, for example, is an example of the benchmark in terms of key sizes and performance for key exchange and signature. This is for post-quantum, and here you have for quantum of the classical cryptography. What you can observe is that just very few outperform the traditional crypto, but all have very large key sizes. This has as a consequence that there is not an obvious and best post-quantum alternative. In addition, the plug and play into protocols is unlikely. There has to be a mixture with traditional crypto as well, and they might compromise to meeting the performance requirements of different applications. So it will have to be evaluated regarding different use cases. In order to select the algorithms, there was by NIST, that is the National Institute of Standard Technology, there was a roadmap for standardization. Last year, they already select the algorithms, the post-quantum algorithms for the standards, and now what the standardization bodies, what they are doing, it is trying to discuss how they integrate into different physical devices, how to certify it, and how to integrate in different applications and protocols. Airbus has already, since the early 2000, it's early in the competition in 2017, has invested on the implementation and deployment of these crypto algorithms together with the integration of different applications. So we have been pioneer, the hardware and software implementation, offering crypto agility. We also were the designers of the first chip of Europe with post-quantum capabilities, and we have driven the implementation on different demonstrations in different scenarios. So this is about post-quantum cryptography. Now let's talk about quantum cryptography. So the idea of the quantum cryptography is to use this new quantum infrastructure deployed in the environment in order to exchange some secret keys that then the different users can use the public transport network to secure the communication. The selling point of this technology is that it will enable the exchange of ultra-secure keys. Authentication should be provided through our public authentication, symmetric authentication, etc. So this is mostly for key distribution. Now there are some No, yes, good. I promise it's going to be short, I'm going to let you do it for your coffee. I think this is very important, and more for the NDSS community, because we really need you guys. So here, so this is what this network will do. Currently, how the protocol will look like, so it uses there are different kind of ways to do this key exchange. One of the most used is prepare and measure, that is based on the BB84 protocol created by Charles Bennett and Gilles Bassard in the 84. It has 3 steps. The first one, encode. the second measure, and the third reconciliation. So where is the trick? Here, Alice will encode the information using a quantum property in photons, like, for example, the polarization. So they use different bases of polarization and encoding 0, 1 in a horizontal vertical polarization or left-right polarization. This information then later on will be measured by both using some measuring bases that can be horizontal or diagonal. Then we have in the encode phase, one thing that is important, if the encoding and base that are used to measure are aligned, you can retrieve the information. If they are not aligned, then you have a superposition and you will have some random value. So how does it work? If you want to exchange some this raw key, Alice will randomly select one of these encoding bases for selecting, for example, in the first bit 1 can be used the vertical or can be used right. In this part, she selects the vertical side. This information is exchanged to both through a quantum channel, and they will measure the bases. If they are aligned, they can retrieve information. If not, they will have an error. Some of this information, which was the basis that they use, will be exchanged through the public channel, and all this information will cross to a part of reconciliation, where you can retrieve the information that it was correct, and in addition, you make some distillation in which you further amplify what is called amplify the privacy by just selected some bits that will be used. As you see, the throughput is very low. So this is a drawback. How you implement this protocol? So there are different kind of technologies. One of the most used is the trusted nodes, in when you have a quantum receiver and transmitted hosted in a secure boundary. And this is something that it is very important here, because these boxes should be in a secure environment. That is why it's called trusted environment. Why? Because currently we don't have we don't have quantum memories. That means that what you transport, you have to store into a traditional memory, and this harm the security. When currently there are some advances in order to develop these quantum memories, in order that you don't have to store into a traditional memory. You also can have other kinds of technologies, like measure device independent, in which is the same trusted nodes, it's just that in the middle is a device called Charlie. And Charlie will do some measures, and based on these measures, the Alice and Bob that are located in the trusted node can guess or retrieve the information. And entanglement, in which they use the entanglement principle. These are in different TRLs. So the current one that they are used is trusted nodes, is TRL 9. So they already products doing this. Entanglement, there are some products, but I think the best performance until now they have the trusted nodes. At the end, what we want is Alice and Bob using this kind of technology. They will have the same secret key. So these links can be deployed in terrestrial and space environment, doing networks that cover globally the different users. Each segment will have advantage and disadvantage. The terrestrial one, they have a higher throughput because currently these kind of quantum links are implemented through optical fibers or free space optics from, for example, a building to building, or from some asset to a mountain across 30 kilometers. But they have a limitation in the coverage, because the maximum distance between two neighbor trusted nodes is about 150 kilometers. Now, the space offered to overcome this limitation by offer a wider capability, usually the satellites that are using the LEO orbit. However, the problem is the throughput, because this throughput is affected by the different environmental conditions, such as weather, pollution, etc. Here in the slides, what I want to see is that I am between 4 different QKD nodes. So these already have some form factors that can fit into the rack. These kind of devices are already in many operators. And they are making some tests, and they are serving already some users. They already have been some demonstration. This was already since 2002, for example, in DARPA. They make the demonstration of this communication. In Europe, it started in 2008 with the consortium of SECO-QC, where they have, for the first time, the trusted node concept. In these Europeans, then later on, were hired to go to Tokyo, where for the first time, it was not only the physical layer, but also on top they have a key management layer. We know that in South Korea, they already have a wide coverage in their metropolitan area. We have in Italy the longest backbone in Europe, covering all their territory. Cambridge 2019, setting records of implementation, and it was already making a demonstration between cross-border communication in different countries in 2021. In the part of space, they have flying several of these boxes in the different orbits. And here I highlight that Airbus was making the first demonstration of this QKD with drone technology, which will enable also to enhance the service provision. But the one that it is currently leading the demonstration is China. China has a network in the terrestrial and space segment, cover all their territory. What is interesting is to see which kind of customers do they have. So they have governmental, critical infrastructure, healthcare, finance sectors linked into these networks. Europe, of course, they wanted also to create a network to secure their assets, also using this technology. So that is why in 2019, the different member states signed a program committing to deploy European infrastructure in the terrestrial space segment to secure all the European assets inland and overseas. What it is, this network is a network of networks where each country has the sovereignty over the implementation, and they have to interoperate with the other nations in this regard with their architecture. They have different security levels. This network of EuroQCI, the European Quantum Communication Infrastructure, should achieve up to use secret level. And as I mentioned, should enable the interoperability. This is the roadmap of the EuroQCI. So Airbus, we have been selected by the European Commission to design and also deploy part of this network. So we design all the network, the end-to-end architecture of the EuroQCI. In this program, I was the chief engineer. Now, in addition, we are making the demonstration of the French part, and we are also the coordinators and leaders of discussion of interoperability between all the nations. But it is not only in the terrestrial part, in the space part, we are the designers of the backbone in the space that is able to exchange this quantum communication. And also we are the developers of the optical ground station in the Earth to receive the satellite signal for this quantum communication information. And it is expected that this will further be integrated into the IRIS², that is the security connectivity program for Europe for different governmental commercial services. This is how the space looks like, just that you have an idea. So we need new satellites with a payload of QKD, and then we have a different kind of optical ground station able to gather this new information, these qubits that come from space. What we are doing, it is the payload. We have also the sources of quantum and the optical ground station, as you see in the figure, and it is a product that will be commercially available already in 2027. So the idea of the EuroQCI is that this will be a network, a new type of network deployed in the terrestrial, space, and in the future in the airborne capabilities, where it can cover and deploy, support the key exchange, and in the future the quantum internet for different applications. But when you talk in quantum, don't only think in the physical part, yeah? Because the physical part is just a small layer, very important and relevant because it somehow also have a strong impact in the performance. But there are several building blocks that are made in the classical world that are the ones that are enable the end-to-end service and the integration and interoperability of this technology with the other secure technologies. Currently, what you can find, and this is something that, for example, different standardization bodies are discussing, like ITU, ETSI, etc., different layers of this network. So you have the physical network. On top, it has the key management. This key management network will manage the life cycle of the keys. On top, we will have a SDN controller that is able to select the route of these keys across the network. And you always will have a manager that will monitor the different elements and ensure that the SLA with the different customers is fulfilled. Remember that all these components must be designed up to use secret level. Currently, it is done like that with distributed key management. What it has a disadvantage is that all the keys are relayed through all the boxes, and this might not be the best option. So that's why Airbus innovate, and we use the best of the quantum technology. What we use is to use this quantum information as a mask. So currently, the secret is not in the keys, so that in the boxes. So that means if an attacker stole one of these boxes, the key is not revealed. What you are using is the ultra-secure information in order to create a mask that can transport the secret key. More information in the barcode. And in the future, we expect to have it to different devices. So just to conclude my talk, as you can see, this quantum technology will have a huge impact in different sectors. One of it is the part of the network and distributed systems. We have already several contributions for the physicists, but now we need you. We need the communication. We have the electrical engineers. We have security engineers in order to turn these technologies into real application. Thank you.
Thank you very much, Johanna, for a very wide, broad talk. I think that was something for everybody, no matter if you're working on communications, if you're working on sensing, on computation, on cryptography. I hope there was something for everybody here. We open up for the Q&A. We have 2 microphones that are positioned on both sides of the room. Please come forward if you have a question. I would like to ask you to introduce yourself first and mention your affiliation if you have a question. And think about the questions. While you're starting to get ready for questions, let me ask one particular one that I am specifically interested in. So you started talking about GPS and spoofing and the way or the role that quantum sensing can play in that. And I'm wondering if you could elaborate a little bit more in which way quantum influences that. Does it make sensing possible in terms of more accurate positioning where GPS would not be available? Or could you elaborate a little bit more on that?
With pleasure. Indeed, so we know that the GPS signal is not always available, and not only for the spoofing or jamming attacks, but also just some lack of communication with the satellite, for example. So then what quantum sensors can bring to the table is that sensors like inertial navigation, they will support the inertial navigation system. So we can have magnetometers, we can have gyroscopes that are more precise, that are based on information that is not dependent of the GNS signal.
So it's about the accuracy, precision increase via alternative sensoring systems to help with that. Okay, thank you very much. I see the first people lined up. I hand over.
Hi. Hi, Johanna. Really interesting talk, and thank you very much. This is Yan Zhao Chen from Zhejiang University, China. So as you talked that quantum computing will be applied to, for example, solving the multi-objective optimization in machine learning, I work on AI security, so I would like to ask what you foresee that this application of quantum computing to AI will affect AI security, or whether there is some inherent security problem of quantum computing itself that will affect the landscape of AI security. Thank you.
Thank you so much. So quantum computers currently they are used and foreseen to further enhance the performance of the design and applicability of the AI itself. Because currently the current capability of processing is limited for the quantum computers, so it is foreseen that the quantum advantage will be achieved by using in a hybrid way, when you have HPC linked to a quantum computer, where the quantum computer will be used to further speed up the learning of the AI, and will be able to generate expert systems in a more efficient way and with less amount of information. So this is very advantageous. Currently, for example, it is used for anomaly detection based on AI, and for image and pattern recognition also.
I see. So what about maybe there is some emergent security issues that may kind of emerge during that speed up process?
Yeah, correct. So the idea is that, for example, if you use this AI applied to security, for example, you can also require less traces of, for example, a crypto execution in order to retrieve or guess the key by analyzing in a more efficient way sidechain attacks such as power attacks, EM attacks, etc.
Okay, thank you very much.
Thank you. We have the second question there. Hi, thanks for the talk. My name is Johanna from the University of Surrey in the UK. So, like Christina asked some clarification, I also want to ask a clarification. I don't work in quantum, so I probably misunderstood. So when you described quantum key distribution, you said that there is no quantum memory to store some of this aspect. So how is this the case when at the same time we have all these quantum algorithms and architectures and so on, and even some quantum computers up to some number of qubits? How come we don't have quantum memory for that? So.
Yes, currently it's something that is underdeveloped, and I think the quantum members will see the light, I think, in 10 years. It is still very raw. So the quantum key distribution, how it works, is like you have a quantum channel, you can establish the key, but then once the key is established, you have to store it into a traditional memory.
But this small, okay, we have quantum computers that are up to some number of qubits, so they do computation like that.
Correct.
Don't those have a quantum memory?
No, they don't have quantum memories.
So nothing has quantum memory. It's not just for,
okay. So how it works in the quantum computers? So you have some problem that you encode and you run it into a circuit of certain depth.
See.
The depth should not be too large, because the
so
qubits you can imagine a qubit as a balloon that is losing the shape of the air through the time. And all the states are just encoded in the surface of this balloon. If the balloon loses the shape, you are losing your information. So that is why you have in quantum computers, you need several physical qubits for making this error correction capability. What happens in the quantum computer is that you have some circuits of certain width, and then you are executing several times. But and once you execute it, you measure
Yes.
and you have a
So you
classical
never
information that
store
you can store
qubit.
it.
Okay.
That is why, for example, multiprocessing attacks in quantum computing doesn't make sense, because you just have one application, you run it, and you let it go. You don't do multiprocessing of different users into a circuit. It's not possible.
Okay. All right, I understood. Thank you so much.
Thank you.
We have time for one more question from the right side here.
Hello, my name is Tian. I'm from University of California, Irvine. Thanks for the talk. So you said that the quantum computing can break the traditional security. So it's just like a need to replace all the existing software that's been deployed to, like, let's say, power infrastructure, satellite system, in the next several years as the quantum computing start, to bring up to speed, because, like, those systems will no longer be secure.
Correct, and that is why there is a concern of how to manage this crypto obsolescence, and that is why the new system have to embed a layer of crypto agility, because when these quantum computers arrive, we need to make a transition, and there are some devices or some systems, you said, that are deployed in very remote areas where it is very difficult to upgrade. So already when we design secure system, we have to think on the upgradability capability to change to a new crypto paradigm. And the first, for example, crypto migration that we can imagine is like to have our current applications, but now with post-quantum cryptography. But you can also have to take into account that if tomorrow there appears a new quantum algorithm like SHORT-2, that is able to break the current standardized post-quantum crypto, we will need to do another transition, and it's better that we are prepared. And currently it is a difficulty for everyone because to have crypto agility, it is not very common.
Thank you. We have reached the end of the session, and I would like to ask further questions to be asked in the break. So thank you very, very much for a great presentation and for being here with us today. Thank you, Johanna.
Real quick, when this session.
We have a break now until 10:20, and at 10:20 the technical session starts in the 4 technical rooms that we have. Enjoy the break.
Thank you so much.